Okay, thank you very much for inviting me here in Húsavík, back in Iceland. It's great to be back. I'm one of the founders of a project that's named Chill Ice, and we had our very first successful campaign earlier this year here in Iceland. So I'm going to tell a little bit more about Chill Ice as a project, but also about some of the preparations that we are actually taking with Chill Ice, but also in collaboration with many other projects and partners to see how we can live on the moon. Let me see. I think I have to press here, right? Yes. So from into the Earth to into the universe. Of course, we are still a relatively small starting project. So at this moment, we are, of course, going into the Earth. But our eventual goal is to dream of going into the universe, with the first priority always going to be human safety, but also to see how we can start up a sort of a link, like a vicious circle, where we actually boost space, but also how we can use space to boost us here as humanity on Earth. And for that, of course, we are doing astronaut missions, just for the improvisation ability, but also for the quick reflexes, for the amount of research that a human can do, sometimes that a robot cannot, but also, of course, for inspiration. I think a lot of us here today are being inspired almost on a daily or weekly basis by some of the things that the astronauts currently are either on board of the ISS doing, or what astronauts in general have been doing over the course of several decades already. But also, before we can actually send humans into space and to do actual astronaut missions, we are training here on Earth with analog astronaut missions. I think my colleague Bailey is going to tell a little bit more also about how we are actually simulating space on Earth. Usually we do this with so-called analog facilities or analog bases. And at this moment there are approximately 30 analog bases all over the world, at least that I know of. There are some more popping up sometimes as well. Most of them are for several missions, and some of them are just like Chill Ice deployable missions. And each of them is focusing on a very different part of space exploration. For example, you have the NEMO base from NASA, which is a subaquatic facility where they can simulate lower gravity environments. Or you have terrestrial analogs, such as the one from High Seas here, which is located on Hawaii. But also Chill Ice is actually a terrestrial analog, so we're using the Earth as an analog for outer space environments. It's a little bit of a shame that you don't see the stars. There was supposed to be a Milky Way on here as well. So, living on the moon, that's the eventual goal. But living on the moon comes with some problems. And just to name some of them, of course, we have solar radiation, but we also have micrometeorite impacts, or meteorite impacts in general. Especially on the moon, we have thermal variances of over 300 degrees Kelvin. And we also have something that's the cosmic microwave background radiation, CMB. Speaking of radiation, I'm just going to very quickly go through some of these problems. Here on Earth, of course, we have a very nice and cozy, yeah, even closer, nice. We have a very nice and cozy magnetosphere, and also to some degree we have an atmosphere which is protecting us from some of the radiation from the sun. And on the moon we enjoy a little bit of the radiation protection from the Earth, but not so much. And especially if we're looking into longer duration human missions into the even further solar system, we are looking at a significant increase in radiation. Currently on the moon you're experiencing about 60 microsieverts per hour, which is about 200 times more than you will experience in a single day here on Earth. So this means that you will need to have a lot of thick protection, especially for the radiation, whether that's lead, whether that's water, whether that's ice or the regolith itself. And the thick protection might be not the worst anyway, because you also need protection from the meteorites, specifically the micrometeorites. They are quite common. There's on average about 1 impactor on every square meter on the lunar surface per day. Which means that it's eventually just kind of a game of chance that you are being struck by one of these meteorites. There's actually a very cool study that was looking into the chances of one of the Apollo astronauts or the lunar lander getting hit during any of their missions. And they came to a conclusion that there was about a 7.5% chance per mission that one of the astronauts or all of the astronauts on the lunar surface would not be able to return home, which is actually quite a lot, and also one of the reasons why we are currently no longer sending humans into space, or at least not to the moon. There are just too many dangers involved. So once again, not just for the radiation, but also for these micrometeorites, you will need some sort of thick protection. And that's not all. As I said, the thermal variances. There's a very cool graph, which is from the lunar equatorial surface, where you can see that there's about a 300 to 320 degrees change over the course of just 28 days, so one lunar day. Which means, of course, if you're standing on the moon, you can also see this when you actually step outside, that the moon is slowly phasing in and out. So you will have 14 days of blinding sunlight, followed by 14 days of very cold, very bitter darkness. Both of them are not ideal. The average temperature is about minus 60 degrees, so maybe some global warming on the moon might not be the worst yet. But still, the thermal degree or the thermal variance in one diurnal day is actually too much, and especially for metal alloys, the growing and shrinking due to these temperature changes will actually cause excessive stress on them, especially, once again, for longer duration missions. And another very cool phenomenon which we have specifically on the moon is actually the result of those four processes, basically, which is something called a regolith. And being a geoscientist myself, I'm fascinated by regolith. It's very strangely angular. So here on Earth, of course, we have a lot of processes which shapes our grains. So if you have a grain of sand, it's actually quite well rounded. Which also means that if you try to build a sandcastle without any adhesive, you cannot really stack it to more than, say, 30 degrees. And then it will sort of sink on in on itself. Whereas the regolith, because there is no wind, because there's no rain, because there's no life, because there are no plants, no chemicals, these grains will be formed purely physically. This means that they have very sharp edges, and they will also have a very large surface area. An almost infinitely large surface area with an infinitesimally small volume, which means that they will react to anything, they will stick to anything, and they will actually kill you if you breathe in a little bit too much. So, living on the moon, it sounds a little bit less exciting than maybe 2 minutes ago. But yeah, still, we have to go there to learn more about where we came from, to understand more about our universe. And yeah, so if we want to go there, as I said, we will need a lot of protection. But it also comes with the question of costs. And it depends, of course, on the rocket, and I think the people from Skyrora here can explain a lot more about it, how much you will actually need. But one rocket launch to the lunar surface is actually, at this point, still very, very expensive. There are some CLPS, commercial lunar payload services, which are pulling down the estimate per kilogram, but currently it's around 1 to 1.8 million US dollars per kilogram that you want to ship safely to the lunar surface. So we better make it a very small, very lightweight habitat. But even a relatively small and lightweight habitat, which is the ISS in this case, which is capable of housing about 13 people for not extended periods of time. It's not even able to withstand the lunar surface yet. So even the ISS is already not good enough to survive with multiple humans on the lunar surface, but it already weighs quite a bit. So with the latest additions, the Vesta module and the European robotic arm, the ISS currently weighs just over 420,000 kilograms. Times, of course, the 1 million US dollar per kilogram to the lunar surface. I think we will need a very, very, very serious group discount here. Otherwise, it will just be excessively expensive. And that's why my role as a geoscientist come into play. Because, of course, on the lunar and also on the Martian surface, there will be much more resources than in the relatively emptiness of lower Earth orbit. Of course, I say relative empty, because as we just learned, it's not completely empty, which is also another problem. Luckily, we don't have that too much yet on the lunar Martian surface. But we can use the soils, we can use the rocks, we can use the minerals, and in some cases even the atmosphere to our benefit, to better human survival. And this kind of in situ resource utilization is also called ISRU. So yeah, as I mentioned, you can, for example, use some of the soils. This is some lunar soil simulant that I used earlier to make concrete blocks to see if we can actually make it into bricks. And then, of course, you also have to break the bricks, which was a lot of fun, to see which one would stand the longest. And what turns out, actually, you are able to build concrete houses on the lunar surface, and they're able to withstand pressures of about 30 to 32 megapascals, which is similar to about 4 to 5 story houses here on Earth, let alone, of course, under the lower gravity of the moon. Another very cool project that I got a chance to be involved in, I call it the Parrot Ice. I think you probably know what this is. No? Okay, so this is actually a part of the lunar surface. This is the lunar South Pole and the lunar North Pole. And if you look closely, you can see some of the little blue dots in here, especially inside the craters. Those are hydroxide deposits, and the most stable form of hydroxide is actually H2O, or water, in water ice shape. So in these so-called cold traps inside the craters, the temperatures can actually drop down to minus 220 degrees Celsius, which makes for a very strange but also very stable form of ice. And that has to do also with the rotational axis of the moon. So here on Earth, of course, we are tilted about 23.5 degrees, which is why we have seasons. On the moon, it's approximately 1.1 degrees. So it's actually almost perpendicular on its axis, which means that if you have a hole, for example here, a crater on the South Pole, which is looking down from the sun side, there will be no radiation coming into the crater. And at the same point, if you have a higher point, like a mountain or a crater rim, you can actually have a peak of eternal light, as they call it, where there's more than 90% of the time there will be sunlight. So this means that you have the option to have water ice, one of the most valuable resources on the lunar surface, very close to an almost unlimited solar energy place. So this is something that we studied in a project which is called Igluna. It was the first ESA lab project, collaboration with, I think, over 10 countries, where we went into the Matterhorn glacier. The Matterhorns might be familiar, the one from the Toblerone chocolate with a dancing bear in front. And we went into the glacier that's actually around the Klein Matterhorn, so the sister mountain. Inside there, we did a lot of science, of course, also on the glacier, and we helped the construction of a small habitat. And inside that habitat, we also studied some of the plant life, and we tried to find some microbes living in the ice, just to see if we can actually use some of those glacial caps. And luckily, we can. But of course, these are just sort of ISRU's analogs. We haven't done a lot of ISRU on the lunar or Martian surface yet. That was until April this year, earlier, when we had a very cool instrument which is called MOXIE. It's an instrument that's hitchhiking with the Perseverance rover, or Percy, on the Martian surface actually, and it managed to extract 5.6 grams of oxygen just in its first hour of production, which is enough to have one adult human breathing for about 2 minutes if they limit their physical activity. So it's not that much yet, but it's a very good start, and it's actually essential also if we ever want to live for longer periods on the red planet. But I think by far the coolest way of in situ resource utilization is not just to use the soils, it's not just to use the rocks or even the atmosphere, it's to scale up a little bit, and it's to use whole structures that are actually on the lunar and a Martian surface. And these lava tubes actually also happen to be here on Earth. And one of the best places to find these lava tubes is actually here in Iceland. Hence why we are, of course, here in Iceland as well with chill ice. Lava tubes are often called caves. This is technically speaking not completely correct, because caves are actually erosional and a lava tube is formed by the lava flow itself. So if you have a lava flow, for example, on the lunar surface at a relatively shallow angle, so about 0.6 to 6.5 degrees, it will of course flow downhill. You do also need a very specific chemical composition, but I will not bore you too much with that just yet. And of course what happens is the outside will be much cooler than the lava flow. The lava flow is around 1400 degrees Celsius, and even when it's in the middle of the day on the lunar surface, and it can be up to plus 180 degrees, that's more than 1200 degrees colder than this lava flow itself. So there will be very quickly a crust formed basically on top of the lava flow. And this crust will solidify and will thicken out, and eventually it will start to form into a sort of a C-shaped tube. Eventually the lava flow dissipates, or it flows onwards, or it disappears via cracks, and all that you're left with is basically that crust on the outside of the lava flow. And that leaves a hollow tube, and with a little bit of luck then we can live inside those tubes. So that's basically what we also did for chill ice, to see if we can live inside one of these tubes. Because of the very rigid walls that they have, because of the thick ceiling that they have, and because of the protective environment that they offer. So as I mentioned before, of course, we have some of those lava tubes on the Earth-Moon system, not just here in Iceland, but also some places on the Moon, for example, close to the Oceanus Procellarum. And the funny thing is actually, because of the lower gravity of the Moon, those lava flows can be a lot bigger, and those crusts can also be a lot longer stable. So actually some of the lava flows that we have on the Moon, or one of the lava tubes, this is in the Mare Imbrium, we've discovered are more than 60 kilometers in length. This one specifically is about 84 kilometers in length. And the holes that you can sometimes see, or the skylights as we call them, openings into the subsurface, can be more than 320 meters deep, which means that it's not just enough to construct a small chill ice kind of tiny habitat inside, but we can actually construct a full lunar city, including an Eiffel Tower, because why not, without having to worry about reaching the ceiling. So yes, they offer a good solution also on the Moon. And as I mentioned earlier, of course, they are also on Mars. So the topographic map of Mars, I think, might be familiar to some. And there was a very cool study done, I think, in collaboration with the Lunar and Planetary Institute in 2018, looking at specifically Alba Mons, one of the largest volcanoes that we have in our solar system. I think this one might be a little bit more well-known, Olympus Mons. It's the highest one, but Alba Patera is actually quite a bit bigger. It's bigger than the country of France, which is very decently sized, of course. And there was a cool study looking into the side of Alba Mons. So this is the western side, like the highest part of the volcano is over here. And all those squiggly lines are rheas and lava tubes with different certainties that have been discovered on the Martian surface. And as you can see, again, in quite great length. So if this is completely correct and all these rheas are indeed lava tubes, there might be some of them which are more than 500 kilometers in length. Another cool feat is this is just one of the supervolcanoes that we have on the Martian surface, but we have quite a bit of them, more of them, and also smaller ones. Which means that if this is happening indeed on Mars in these quantities, and these other volcanoes, which sadly have not been researched as much yet, there actually might be a lot more lava tubes on Mars than here on Earth. So if we want to study lava tubes, why go to Iceland? Just go to Mars instead. And of course, one of the famous roadmaps, I think, hopefully this timing will still be okay. I think we're already scooching a little bit up towards this side. But one of the ideas is to go via the Moon to Mars. And if we can survive inside those lunar lava tubes, then we can also survive in the ones on Mars. So it's like a safe practice ground. And we're actually already getting quite close by. So this is the landing ellipse of Perseverance in the Jezero crater, which is this whole thing with a very famous delta here, which they're also trying to look at. But very close by, actually, here in northeast Syrtis is also a volcano, and there have also been lava tubes found. So we are actually already about 80 kilometers far away from a Martian lava tube already. Speaking of the whole distance, which is, I believe, currently about 165 million kilometers, we are already very close by. But it is still a very big problem, because as you can see, these lava tubes are quite steep and can be very hard to get into. This was actually on the Hawaiian High Seas mission, where I was a lead scientist in 2020, but I will leave more of High Seas for Bailey as well to talk about. The thing is that I want to talk about the problem. So even if we get very close to those lava tubes, we still have to get into them. And as I said, they can be drops of more than 300 meters, so we better have to prepare. And we also need to study the accessibility. There are apparently at least some moral problems with sending humans into an unknown crevice on the dark side of the Moon, not ever knowing if they come back. So we need to study how these lava tubes are looking like from the inside, preferably without having to go in. So this was what I was trying to do, at least in Hawaii. I was using magnetometry to study the subsurface. Magnetometry is maybe well known for the metal detectors. So if there's material which is higher magnetically conductive, you will actually see a sort of spike in the magnetic activity or magnetic field of the Earth. And As I mentioned already before, these rocks that we have on Hawaii, but also here on Iceland, and also actually the ones on the moon and on Mars, they need a certain composition, and they need to have a higher composition of metals as well. So basically what I was trying to find in Hawaii is that there is a sort of constant positive anomaly because there are constantly these types of minerals present. The only thing is if you want to have a negative anomaly, you need to have a lack of minerals, therefore a lack of rocks, and therefore the presence of a lava tube. At least that was the theory. So I tested it, and it worked, luckily enough. And we actually found that there are some deviations in the magnetic field of up to 12.5%, which means that even if there is no active magnetic field, like of course on the moon or on Mars, there is still an observable difference even in the latent magnetic field or the magnetic field that could have been originated just from the flow with the preferred orientation of these kinds of minerals. So this one will also work. And it's a crucial way actually to help understanding our planet. So as I mentioned before, we are going into the Earth to go into the universe, but also we are going into the universe to learn more about the Earth. And that's the slogan of Chill Ice. Chill Ice, it's an acronym. In space, we love our acronyms. So it stands for the construction of a habitat inside a lunar analog lava tube. And of course, we are in Iceland. It was founded in 2018 in collaboration with EuroMoonMars and the International Lunar Exploration Working Group. We have a very cool logo, as you can see here. That's actually our logo. This is our mission patch with the 16 countries that were working with us. And our mission objectives were, first of all, of course, to discover suitable lava tubes. Where can we build a habitat and where can we build such a settlement? But also, of course, to study if we actually want to live there. I mean, that we can live there is one thing, but that we actually send humans in without having them kill each other is another thing. And we were focusing also on all of this being in simulation. So the astronauts, this was actually the final briefing of the first mission, just outside the lava tube. And they were limited, of course, with their suits in their visibility, in their dexterity, in the maneuverability, but also in their time. So we based on the Apollo EVA time of about 8 hours. And they had to move the habitat inside the lava tube, and they have to construct it there, or inflate it actually. But also have to carry the supplies in. They have to carry the solar panels, the power supply, the communication system, the Wi-Fi antenna, and I'm forgetting a whole bunch of stuff, and they only had 8 hours to do it. We were going here in Stefanshellir. I'm hoping that I'm pronouncing the Icelandic names right. I'm sorry if I'm not doing so well. So it's actually located in the Hallmundarhraun lava field in West Iceland. And we were going, I was hoping that I would have a zoom in. Yes. So you can see the profile here. We are going to the easternmost gallery of the Stefanshellir cave system. It's actually a 3 cave system, but the third cave is called Hulduhellir, which means hidden cave, and we cannot go in because it doesn't have any skylights. So we were going to a large gallery here on the eastern part, where we would have a subsurface habitat, and of course also our antennas and power source on the outside, because of course inside the lava tube there is not a lot of solar energy. Just to give you a little bit of an idea where we were exactly, we were here near Surtshellir. This is the Langjökull and the Eiríksjökull, the largest tuya in the world actually, also fun fact. This is what it looks like from the top. It's actually not per se this dark, but it has to do with the moss that has sadly died there. This moss is protected, but there are a lot of tourists as well in this area, and they walk over the moss, then it dies, and then you can get the darker colors of the rocks actually. It was also one of the reasons why we chose these caves, because of course lava tubes are very fragile and protected environments, and these were already quite badly damaged by tourists in the past, so it would be a little bit safer to construct our habitat inside. Our MCC was actually located here, near to the Húsafell Activity Center, so it was about 14 kilometers away, which is of course a little bit less than to the actual lunar surface and MCC. We were using this habitat. It's called ECHO, Extreme Cave Habitat 1. It was designed by students and faculty members from the KPU in Canada, the Wilson School of Design of the Kwantlen Polytechnic University. And as I already mentioned, it's an inflatable habitat. So as you can see, there are multiple sort of ribs which are inflated, and that makes it into a super portable habitat. The whole thing weighs less than 16 kilograms. You can actually check it into your checked-in luggage on the plane and carry it by hand. I actually did this already twice now, and it actually works. It's quite fun. Of course, we also had spacesuits. Our spacesuits were coming from Spain, from the Australian Interplanetary Agency. They're actually also a cave analog habitat, but they are focusing on limestone caves and more on the speleological part. But they're a very cool partner for us as well, of course, because we're also in a sort of cave, in a lava tube. And we also had a collaborator from the Netherlands, which is the Lunar Zebra. It's a very cute, very nice little rover. It's supposed to be as a swarm. Let's see if I can start the video. Yes. As you can see, it's not the fastest, but because of its legs, it can also conquer terrains which a normal wheeled or a tracked rover is not able to do so. And the construction of these Zeros are relatively cheap. So you can actually make 100 of them and you can drop them into a lava tube on the moon. Maybe half of them don't survive, but the other half does. And they can actually explore the cave without having the need to come back, which you would definitely want if you have a multi-million-dollar robot or rover. Another sponsor of us, GoPro, is located on top of the Zebra. And we focused, of course, also a lot on the insides of the cave. Kind of surprised the video works. It's a very high resolution video, and you can see some of the lava droplets which are coming down. These lava droplets are also very protected here in Iceland, and they're a very unique feature, which are quite rare even on lava tubes here on Earth. And they are not real stalactites, even though they look a lot like stalactites, but of course this is not a cave, this is a tube. So these are actually tiny lava tubes on themselves. They were formed when the lava tube was already formed and a new eruption put another flow of lava inside. It sloshed up to the sides, and when it started dripping down from the ceiling, it solidified. So a lot of these are actually also empty or hollow on the inside. They're just like a tiny little lava tubes inside a lava tube. It's very cool. We also took some rock samples, of course, with the permits and with the help of Space Iceland to actually get those permits. And we challenged our astronauts to make up silly names for the rocks because that makes it just much more rememberable. So we have, for example, Purple Cha-Cha over here because it's purple. We have Big Cheese because it looks a little bit like some of the Swiss cheeses. And yeah, we had a lot of fun also with the naming of these samples. As you can see, the rover here, poor Zebra, is lying on its back, being operated on. And we also are working on an AR detection program, basically, to see if we can recognize the astronauts even in the dark. And we are looking to expand this program also to recognize features inside the cave. And of course, because if you're on the moon, you don't have GPS. And even if we were to have GPS in the cave, there's no radiation, so there's no GPS. And it can be very hard to localize yourself within such a cave. And if there are just a couple of hundred features within the 3D model of the cave, for example, if you get a cut or you fall down and you need to be rescued, you can sort of scan the environment and then it will just recognize from the system, okay, so it's 20 meters to Purple Cha-Cha and it's 5 meters from the hockey field. So I know exactly where I am and I know exactly where the 8 troops must be sent to. And we also have a GIF of our astronauts walking on the surface. As you can see, it's detecting astronauts, which is just a fun first step, but we're actually going to expand this as well. You can see the habitat in the back here. So this is inside the Stefans Hetlier lava tube. Yes, I think I'm just going to skip this. And this was our very first crew. So we have a Polish astronaut. We have our Swiss commander and a Scottish engineer who was working as one of our scientists as well on the mission. And he is also the one who is helping us develop the AR program for the detection of astronauts and other things. So we locked these astronauts up inside the cave for 55 hours each. We had 2 missions during our campaign last summer to see if they could survive. And as you can see, this was him after the mission. He is still smiling. He is still alive. So I think we did pretty good job. They were very tired though afterwards. They found it very hard to sleep, which was one of the problems actually we had a little bit with the insulation. So the insides of the caves are of course the average annual temperature, which is around the 0 point here in Iceland. So they had a very cold time inside the cave as well. but they are still laughing. So I think we did well. Of course, we had a lot of sponsors and collaborators, and I would also definitely like to thank all of our sponsors. I think they're still flying in, who helped us with the spacesuits, with the habitat, with the communication systems, with the food, with the supplies, and of course also some monetary funding. And yeah, after the success of the mission, we did a lot of outreach. We did a lot of publications, as I already mentioned. We managed to bring the habitat as well to some other locations. So we took the habitat with us to Bulgaria. We took the habitat with us to Marbella in Spain for a space and underwater tourism summit. We went to some radio interviews, TV interviews. We were keynote speakers, TEDx speakers. And of course, we also had some outreach events at the cave. You can see me kneeling down close to Stefan's head here. This was just after the second mission. You can see the entrance to the cave here. And there's actually still the power supply system standing on the surface. And of course, the reason why we do what we do is to push humanity outside of their comfort zone. So currently our comfort zone is here, but we definitely have to look on to see what we can actually learn more from the universe. Again, to also help people here on Earth. And that is often also a matter of serendipity. It is finding what you needed without knowing that you were even looking for it. And we can already see this in the technologies that we have gotten from space, like the solar panels. There were solar panels for almost 200 years. But it was not until we actually decided to go into space that we needed higher efficiency or solar panels. But also the cameras that we are using right now are actually based on space technology as well. Of course, the internet, which we are live streaming right now here, would not have existed, or at least not in the way we know it right now, without space technology. And it's that kind of impact that we are creating, not just on ourselves here on Earth, but also to our future selves. And it's also a matter of vulnerability, or actually mitigating our vulnerability, because we are here as one species on one Earth, on one planet, which makes us vulnerable. And especially speaking from geological perspective, we have had multiple mass extinctions already. We have had 5 of them in which over 75% of all living species at that moment died out. One of the very famous ones, of course, is at the KPG boundary when there was a meteorite strike and all the dinosaurs died out, or actually all of the land-dwelling creatures up of north of 25 pounds basically died out, which of course included the dinosaurs, but would nowadays also include us. And we can basically mitigate that just by going into the universe and going to other planets as well. And it's really a game of survival basically. And every organism that we know of has the drive to survive and has to drive to ensure the survival of its species. And we are basically the very first species of weird apes to actually be able to move outside of this Earth, move outside of our comfort zone, and mitigating problems such as these mass extinctions by going into the beyond. That's basically the end game, also for Chill Ice, to reach for the stars, to go into the universe by going into the Earth right now. From into the Earth to into the universe. Thank you. Are there